The universe of systems is divided into two worlds. One world is a world of predictability, simplicity, and order. And the other world is a world of complexity, disorder, unpredictability, and chaos. The first world is the world of linear systems, and the second is that of nonlinear systems. Boy, that intro just gives me chills. So today's lecture is on linear systems, the first of these two worlds. And the principal properties of linear systems are additivity and homogeneity. So we need to define these two. If a system has additivity and homogeneity, it is a linear system. And we're showing the angels here because linear systems are extremely well behaved. And they're extremely well behaved because of additivity and homogeneity. So let's now learn about these properties. So here is the definition of additivity. If an input x1 of t acting alone produces output y1 of t, and if input x2 acting alone produces output y2, then if we put in an input which is a combination of these two, x1 plus x2, we will get an output which will be a combination of the two outputs we found before, y1 and y2. Here is a graphical interpretation of the additivity condition. So on the left we have inputs x1, x2, and x3 equals x1 plus x2. And we're going to conduct 3 experiments. We're going to use the same linear system. And we'll put each one of these inputs into the linear system. And then we'll get the outputs. And the output in response to x1 is y1, the output in response to x2 is y2, and the output in response to x3 is y3. The principle of additivity says that we can find y3 simply by adding the outputs that we found from the first 2 experiments, y1 and y2. Let's now look at the property of homogeneity. So let's suppose a system has homogeneity. Then if input x1 acting alone produces signal y1, then input x2 equal to k times x1 acting alone will produce an output that is k times the output we found before, y1. And this is true for k being any arbitrary constant. So a simple way of looking at this is if we put in twice the input, we will get twice the output. That is the property of homogeneity. Here is a graphical interpretation of the property of homogeneity. On the left we have inputs x1 and x2 equal to 2 times x1. We put both of these inputs into the same linear system. The outputs, in this case, are y1 and y2. And because the system has homogeneity, output y2 is twice output y1. These properties of linear systems are so important that we've invented a term that stands for both of them together. So homogeneity and additivity make up the property called superposition. So if a system obeys superposition, it has homogeneity and additivity. Here is the mathematical definition of superposition. It says that if input x1 produces output y1 and input x2 produces output y2, then if we make a new input by forming a linear combination of x1 and x2 as follows, x3 equals k1 times x1 plus k2 times x2. Then the output in response to this input will be y3 equal to k1 times y1 plus k2 times y2. These properties of linear systems are extremely important throughout the entire class. And the one I'm giving you on this page is also very important. I almost cannot stress enough how important it is. If a system is linear, its output must be the sum of two signals. One is the output due to the initial conditions acting alone. The other is the output due to the input x of t acting alone. So we can, if you will, do two experiments. One where we just see how the output responds to the initial conditions, and another where we just see how the output responds to the input. And then once we have the result from those two experiments, we can simply sum them together, and we'll find out the output in response to both initial conditions and the input. This property and the property of superposition do not hold for nonlinear systems. The output due to the initial conditions acting alone is referred to as the zero input response, and the output due to the input x of t acting alone is referred to as the zero state response. Throughout this course, we'll develop various methods to find the zero input response and the zero state response. The system's output due to both initial conditions and to the input is referred to as the total response. And for a linear system, the total response is the zero input response plus the zero state response. Throughout the course, we'll be referring to total response, zero input response, and zero state response frequently. You should be sure to understand the definitions of these terms. In this course, I've found that students often don't know when a result is really important. And since your instructor thinks almost everything in each lecture is really important, often I don't spend enough time emphasizing. But I'm using a special device here which I'll use a few times in the course, and that is the frame of importance. So when you see the frame of importance, you'll know that I've found something to be really critical to your understanding, and I'll try not to use it too much. You should be aware, though, that sometimes a result will be important or very important, and I won't bring out the frame. In this lecture, I'd also like to highlight the zero input response and the zero state response. So the zero input response, once again, is the system output due only to initial conditions. For such an experiment, the input x of t is equal to 0, and so it has no effect on the output. On the other hand, the zero state response is the output due only to the input x of t. The initial conditions, in this case, are 0, and so they have no effect on the output. The sum of the zero input response and the zero state response is the total response of the system. It's the output in response to both initial conditions and the input. Should note that this property does not hold for nonlinear systems. For linear systems, the property of superposition also holds for the response due to initial conditions. Let me illustrate this with two examples. Let us suppose that we have a linear system and that we conduct two experiments. In the first experiment, the initial condition y at time 0 is equal to 1, and in the second experiment, the initial condition is equal to 2. The response in the first experiment is shown in the upper graph. Because the system is linear, the response in the second experiment, shown in the lower graph, is twice as large as that found previously. This is a simple example of the superposition property of linear systems with respect to initial conditions. Let's now look at a bit more complex example. A ball is thrown straight up 3 times. This system has two initial conditions: initial position, y at time 0, and initial velocity, y dot at time 0. These are all the initial conditions you need to define the ball's motion. This because the ball's motion is described by a second-order differential equation, and therefore we need two initial conditions. We conduct this experiment 3 times, and shown below is a table showing the values of y0 and y.0 in the 3 experiments. The response to experiment number 1 we label y1, and the response to experiment number 2 y2, and of course for number 3 we label it y3. Now superposition will say that there must be a relationship between y3 and y1 and y2. What is this relationship? Note that the initial conditions for test number 3 are those for test number 1 plus twice those for test number 2. This is illustrated in the little box in the lower left. The initial condition for y in test number 3 is 5, and that is equal to 3, the initial condition in test number 1, plus 2 times 1, the initial condition in test number 2. The same holds for the initial condition y dot. 4 is equal to 2 plus 2 times 1. Because of the property of superposition, we can then say that y3 must be equal to y1 plus 2 times y2. So now we've reviewed some of the important properties of linear systems. In our next lecture, we'll view some examples of this type of system.